This helicopter will never fly unless I can successfully redesign the intake and this two-stroke exhaust to have it package all underneath my carbon cowling. My name's Callie, I'm the OKS engineer, let's get into it. Well, I've managed to back myself pretty deep into a corner when it comes to packaging everything underneath this cowling. And usually what that means is compromises will have to be made, and you have to be extremely clever to try and reduce those compromises as much as possible. I think it's also extremely important to note that CFX has their own set of design criteria and limitations that they are following, which are driving those same compromises that I'm making just for different reasons. And so if I'm doing something different than CFX has done, it's likely because they have some constraint that they're following. And I can assure you, between the hundreds of aircrafts that are flying and the thousands of hours that they've flown, that CFX has done everything they can and has proven out that it is safe. The last thing they need is an accident to happen to tarnish their reputation. I respect them, their engineering choices, and everything that they have done. And it is for those reasons that I've chosen this helicopter specifically, the Mosquito, as a starting point for this project, and why I haven't and don't plan on making any modifications to the fundamental function of this helicopter, including the drivetrain and controls. It is solidly built with a very good track record. The two big things I'm tackling today are the exhaust and the intake. For the exhaust, CFX uses the factory Y pipe from the engine manufacturer to go from two cylinders into one, and then they built an exhaust that goes laterally to the helicopter for a couple reasons that I can only assume. One is to keep the CG as forward as possible because it's already a rear CG helicopter, and two, they don't have the restriction left to right that I do, and they don't mind if that exhaust sticks out to the sides. So for me, this factory Y pipe has got to go, and it's got to get redesigned so it directs the exhaust more in the direction that I need it to go, and the factory CFX exhaust has to get redesigned because I need to favor a more forward aft direction for my exhaust than a left to right. For the intake, CFX uses a panel filter and kind of an intake box that gets mounted to the side of the helicopter, and it goes through a couple tubes through a MAF sensor and then into this like intake Y. Honestly, I was hoping to use some of these components, but as you can see now, it won't fit in the cowling, which means this is a heck of a lot tighter than even I thought it was going to be, and I'm going to have a heck of a time trying to package all of that into that corner. So right now, all I really know is I have a problem. I don't know how much of a problem or how I'm going to fix that problem until I can get all of these parts scanned and into the computer so I can start playing in 3D space. For that, I'm going to be using my tried and true favorite tool in the toolbox, the Einstar 3D scanner. I'm going to go ahead and get the exhaust and that Y pipe scanned in CAD so I can understand the dimensions that go along with that and their tried and true exhaust. And I'm also going to get the engine basically envelope scanned and in position of the rest of the fuselage so I can just see how much space I have and what I can do with that intake. Now, unlike a four-stroke, a two-stroke doesn't have valves controlling when air and fuel come into the combustion chamber and when exhaust can leave. Instead, it uses ports in the cylinder, and the exhaust pipe plays a huge role in how well the engine breathes. That's why I can't just haphazardly start cutting up this exhaust to get it to fit underneath the cowling. A two-stroke exhaust isn't just something to get gases out, it uses pressure pulses to basically regulate how much air and fuel get into the combustion chamber and how much exhaust air gets out. These pulses are similar to the shock wave that large explosions send off. The air isn't moving, but the shock wave brings a massive amount of energy with it. Those shock waves can also be reflected, and they behave differently based on the geometry they interact with. And that's why in a typical two-stroke exhaust, there's a diffuser at the beginning of the exhaust and a cone at the end. When the exhaust leaves the cylinder, it creates that pressure wave. That wave travels down to the end of the pipe, is reflected back, and can help pull exhaust out of the combustion chamber while also pushing some of that fresh fuel and air mixture back into the cylinder before the port closes. With that understanding and also knowing how fast that pulse travels through your exhaust, you can start to design the overall tuned length for a given RPM so you can time that pressure pulse to come all the way back and close that exhaust port exactly when you want it to. That is a very high level of how two-stroke exhausts work. I'm not going to go into very much more detail. If you're interested, AU Mechanic and Driving for Answers both have phenomenal videos describing the subject, and I'll link them in the description. For me, the goal is to define an optimal tuned two-stroke pipe length using the CFX exhaust as kind of a baseline and the 6,000 RPM operating condition of the helicopter. Once I have that tuned length, the next challenge is going to be to try and figure out how to package underneath the cowling. After scanning the CFX exhaust and measuring the tune length, it came out to about 50.2 inches with a tuned RPM of about 6,100. Considering my RPM target was 6,000 and the fact that I plan to ceramic coat this exhaust, which will inherently increase the speed of sound through that increased exhaust temperature, I needed to change the tune length by about 200 RPM, or increasing the overall length by about 1.5 inches. I chose to add most of that extra length to the Y pipe to give it a more gradual merge between the two cylinders and get the exhaust going in the right direction. Individual exhausts would have been better, but I'm already struggling to package one exhaust, so a second isn't even an option. Both the engine manufacturer and CFX use a Y pipe, so it isn't like I'm headed into an unknown here. The CFX exhaust uses a belly stinger, and although that's not ideal, in some cases you can do that if packaging requires it, and I'm not ruling that out. My goal though is to use a more traditional stinger that exits through the end of the exhaust cone. Now, after a whole lot of screwing around, this is what I've come up with. I'm not quite sure how I'm going to manufacture this thing yet, but as any good engineer, if it works in CAD, it's going to work in real life, right? I may even screw around with hydroforming or a couple other unique manufacturing methods. Let me know what you guys think on how I should make this exhaust, and please give me some suggestions. Packaging the exhaust in here was pretty tough, but something tells me this intake is going to be even harder. So let me take a second to basically outline the design requirements so you have an idea of what I'm working with. First and foremost, all of this has to obviously fit underneath the cowling. So that's challenge number one. Challenge number two is I need to draw air from outside the cowling so that it is cold and fresh and not hot from everything inside. That imposes its own issues. I don't want that exit to be in the portion of the cowling that's removable. That'll just mean taking on and off the cowling is a nightmare, and it's going to have all sort of mating issues. The only other option is to pull air from the cavity I created from the permanently installed cowling and the original fuselage. And that all sounds fine, but something tells me it's going to take my CAD skills to the very limit. Assuming we can get air in through that cavity, the next step is to get it through a filter. Now, this imposes its own challenge. This filter is literally the smallest filter you can find that will flow the amount of air that this engine requires. I can't go to a round filter, that takes up too much space, so I'm stuck with a panel filter. This panel filter basically consumes all the area that I have in this location to fit an airbox. And the airbox can't just be the size of the filter. Through this entire path, there can't be a single location where the cross-sectional flow area is less than the combined area of the two throttle bodies, and that happens to be about 6 inches squared. Assuming I can maintain that requirement, I then need to get out of the airbox and through a mass airflow sensor, which one is not small, plus they really like to have like an undisturbed length before and after the mass airflow sensor, which frankly is just not going to be possible. And then I need to turn and get into the individual throttle bodies without having too tight of a bend radius. Oh, and I forgot one more thing. The engine moves, and in this application, that motion will be kind of fore-aft from it rocking. So any ductwork that goes in that same direction will basically load up and inhibit that motion, and that's a bad thing. So you would typically design some sort of an S-bend into the system to add some compliance to take up that movement and not transfer those loads into everything. I wanted to give you guys a quick glimpse into what it took to actually design these things. Starting with the intake, you can see that basically there are no normal or perpendicular planes anywhere, and the design tree is basically a mile long. This was insanely hard to try and place everything and get everything in the correct locations. Starting with the front, this was my idea to get the air into the airbox. This will basically be a duct that will sit underneath the surface of that cowling, and that will direct the air up and into the first forward portion of the airbox. You can see here how it will fit against the fuselage, and unhiding the outer skin shows that everything sits behind the cowling. The second half of the airbox and the intake Y is a similar story. There are no square surfaces and there's basically nothing to reference, so I relied heavily on the 3D scan and modeled everything based off of it. Air exits the airbox at the bottom back corner with a nice smooth entrance and immediately turns upward to go through the MAF sensor. From there it goes into the Y, which had its own challenges due to the tight proximity to the cowling and the very tight bend radius as I went into the throttle bodies. Each throttle body has a nice big trumpet to help induce air into the engine in the event you were going to bolt a filter directly to it. Since I was using a remote filter and ducting, I decided to take advantage of that extra depth and the smaller diameter and actually recess my Y into those throttle bodies to help with the clearance to the cowling. But even with that, the clearance was still pretty tight and the bend radius was still quite small, but these are the compromises I had to make given the constraints I was dealing with. The design's close enough for a first shot, so we're going to get these things printed out and see if it fits in real life as good as it fits in CAD. All right, and here it is. And actually, guys, I'm pretty stoked and proud of myself with how this thing turned out. As you can see, there will be kind of a sleeve that slips in between the cowling and the fuselage that will direct the air from a NACA duct that's going to be cut into the outside of here. So that air gets directed into the forward portion of this airbox. That airbox is tilted and it places the panel filter at the perfect angle so that I can get it all situated and fit it in here. And you'll also notice there's a triangular shape on the top and bottom here. That is that 6 inches squared volume that I needed to not restrict the air coming into the forward portion of this airbox and then through the panel filter. Then the other side of this panel filter just catches it and once again has a similar triangular size shape to once again maintain that cross-sectional flow area. I then got my S-bend out of this thing by exiting at the bottom portion of this forward airbox. It turns pretty sharply and goes through my MAF sensor. Yes, it is not in a straight length and it won't be. There's just no way around this, and actually I don't really plan on using that mass airflow as an input for the tuning of the engine anyways. So we can get into that later. But then it goes through this Y. The Y then goes directly into the intake port, and as I mentioned earlier, I did neck it down so that it would fit and get a better bend radius given the diameter, and that will go right there. So now I get all my compliance from that engine rocking back and forth. I get a panel filter that's internal to the cowling, so it fits all underneath of that, and I think I did a decent job at getting this all packaged in here. Now, this is all 3D printed. It is just a prototype. There's actually some further design that I need to do to make this all fit right, but it will be 3D printed as the final part, but not out of this material. There's some engineering grade material that far exceeds most plastics, and it will do just fine in the environment that is in this engine bay. The front little duct that directs the air from the NACA duct, that will be carbon fiber. So I'm going to go ahead and make a mold for that, lay that up, and then I will bond that into that cavity underneath this cowling. So that will be carbon. But yeah, everything else will be 3D printed. I'll probably paint it and make it look pretty anyways. And that will also protect it from oil and anything else that gets on the actual material. The exhaust Y is perfectly symmetrical and has a much better blend between the two cylinders. It also gets the exhaust directed in the correct direction, which is what I needed. And although I haven't prototyped the exhaust, that will do a loop and go forward as you saw in the CAD model. This will also be 3D printed, except out of metal, actually Inconel. So I'm going to have a friend of mine print that up for me, and that's what I will be using for this actual part. And one last little surprise for you guys. I'm honestly shocked no one's ever mentioned it, but I designed and printed a fin to close the gap between the cowling and the boom, and I think it just really ties everything together. This one damn near killed me though. I could not get CAD to work, and it just was an absolute nightmare, and I'm pretty stoked that it finally worked. No joke, I have at least 40, probably closer to 80 hours of CAD in all of these things that I've done, and it's largely the reason that you guys haven't seen a video in a while. The fin will be made from carbon fiber, and something tells me that mold is going to be a challenge. Curious to hear from you guys if you like what I've come up with. If you do anything different, your comments are always valuable. I think all of the design, knock on wood, is finished for this helicopter. It's just fabrication from here on out. I do need to get all of this ready for paint. That includes touching up the dash. I need to figure out where I'm going to cut access panels into the cowling so I can do pre-flight inspections. And I also need to get this radiator mount and shroud all touched up and fitted with the radiator in it. I will be at the Oshkosh Air Show the entire week, Monday the 20th through Sunday the 26th. I'd be more than happy to meet and hang out with any of you. Feel free to reach out at the Okayest Engineer on Instagram or Facebook, and I will see you there. I'm not quite cool enough to be on a YouTube panel yet, but maybe one day. Go build something cool, never stop learning, and we'll see you on the next one.